we're going to be using our beloved Framingham dataset to look at the association between smoking and death across levels of age. Now we're going to use the age for cat variable that we've created in previous sessions. And here's the code, which is also included in the handout for this session. So let's open up our dataset. Here's the Framingham dataset. Here are our age categories. So age for cat is set to missing, and then we replace it with 0 if the person's less than 40, 1 if the person is 40 to 50, 2 if the person is 50 to 60, and 3 if the person is older than 60. First thing we want to do is just make sure that the 2x2 tables can be calculated for each age category. So let's go to Statistics, Summary Tables and Tests, Tables, 2A tables with measures of association. Our row variable is going to be death. Our column variable is going to be cur_smoke1. And we're going to calculate those 2x2 tables by age for cat for each level of age. And here are our different age-specific 2x2 tables. Now it's possible that once we stratify on age, there's no more confounding by age, and now the relationship between smoking and death will be similar across levels of age. On the other hand, it's possible that we have effect measure modification, and the relationship between smoking and death is different for people of different ages. But now we've got to decide, are those stratum-specific estimates for the relationship between smoking and death different by levels of age? What test should we do? You got it. We're going to use that test of homogeneity. The null hypothesis is that the stratum-specific estimates are homogeneous. There's no effect measure modification. Our alternative hypothesis is that at least one stratum-specific estimate is different from the others. It doesn't mean that all the strata have to be different from each other, just that one is different from the others. For this test, the degrees of freedom is the number of strata minus 1. After we've conducted this test of homogeneity, we're going to get a p-value. If it's a large p-value, we will not reject the null hypothesis and conclude that there is insufficient evidence of effect measure modification, in which case we'll report stratum-specific estimates or we'll calculate a Mantel-Hansel summary measure. However, if we get a small p-value from this test, we will reject the null hypothesis and conclude that effect modification is present, in which case we'll report stratum-specific estimates or a standardized measure. Let's go ahead into Stata and see what happens when we calculate these stratum-specific estimates and a test of homogeneity. So in Stata, we're going to go to Statistics, Epidemiology and Related, Tables for Epidemiology, Cohort Study Risk Ratio. Our case variable is going to be death. Our exposed variable is going to be cur_smoke1. And then we're going to go to the Options tab. And we're going to stratify on age for cat. And here are our results. Now what you can see is the results that we showed you last week, in which we see that all of the risk ratios are greater than 1. The risk ratio for death is higher among smokers than non-smokers for all age groups. And the risk ratios range from 1.18 for people greater than 60 years of age to 1.79 for people under 40. We've already seen that the crude estimate shows that overall the risk of death is 1.07 times greater among participants that reported smoking at visit 1 compared to those who were not current smokers at visit 1. And that if we adjust for these age categories by using the Mantel-Hansel formula, the risk of death is 1.38 times greater for smokers than non-smokers after accounting for age. In the previous session, we concluded that there was evidence of confounding by age because the 1.38 was different than the 1.07. Now, once we've addressed issues of bias and confounding, we need to consider whether our summary estimate is due to chance. Do the risk ratios differ by age group simply because of sampling variability that arises when several estimates are taken from a sampling of the same underlying distribution? Or are these stratum-specific estimates different because they indicate that the association between smoking and risk of death is truly different at different ages? In other words, does age modify that association between smoking and death? Now, when we do this formal test of homogeneity, we're testing whether they vary by age because of sampling variability and there's no effect modification, or whether these evidence of stratum-specific estimates is beyond sampling variability and is in fact effect measure modification. Now, I've highlighted the test of homogeneity here. Our chi-squared value had 3 degrees of freedom because we had 4 age levels. The number of strata is 4 minus 1, so 3 degrees of freedom. We get a chi-square value of 19.107 and a p-value of 0.003. What do you think our conclusion should be? And how should we present our results? Well, since the p-value was less than 0.05, we would conclude that there is evidence of effect measure modification. And in terms of how to present our results, we say that reporting the pooled Mantel-Hansel estimate is not appropriate. We can show the stratum-specific estimates or a standardized estimate. What would you prefer to do here? Well, in this example, it's helpful to report these 4 stratum-specific estimates that we see above. However, imagine that we were looking across levels of variable with several strata. Or let's say that we decided that we had to worry about not only age, but age and socioeconomic status and sex and weight. We could have tens of estimates, and it would be hard to get a big picture understanding of the relationship with so many stratum-specific estimates. So in that setting, we very often would like some type of summary measure. But we just said that we cannot use the pooled Mantel-Hansel estimate. So what we'll do is come up with a summary measure using standardization. Now, standardized estimates for smoking and death will be adjusted for differences in the age distribution between the smokers and those who are not smokers. So the standardization can be used for confounding or for effect measure modification. Here we'll use it to address both at the same time. So in order to calculate the association between smoking at visit 1 and the risk of death after adjusting for age by standardizing, we can standardize to the total population. So let's do that one first. Now in Stata, we have to tell it that everybody in our sample should be weighted equally. So we have to create a variable that's equal to 1 for all 4,434 individuals in the sample. It's just a formality in Stata. So let's create a new variable called all. I'm going to do gen all equals 1. The next thing I'm going to do is go back to our estimator for cohort studies. So we're going to go to statistics, epidemiology and related, tables for epidemiologist, cohort study risk ratio. And you'll see that we still have death as our case variable, cur-smoke1 as our exposed variable. We're still stratifying on age for cat. But now, instead of using the Mantel-Hansel weights, we're going to use our new variable of all. So we're going to go to the user specified variable and click all. And here are our results. Now what you can see here is that all people of all ages were weighted equally. Everybody got assigned a 1. And our crude estimate was the same as always as 1.07. But when we standardize to the total population, our point estimate is now 1.32. And the way we interpret that is that we say in a population with the age distribution of the total population, the risk of death is 1.32 times greater among smokers than among non-smokers.